Hey, what's up, guys? Uh, so this time let's take a look at another very classic problem uh, on LeetCode. Number 410, split array largest sum. Um, so let's take a look. So you're given like an array of numbers, and you need to split this array into m groups. And among all those possible ways of splitting this arrays into m groups, you need to find the minimum of the largest sum among those m subarrays. Okay, so basically, so for example, this one, right? So it said there are four ways to split numbers into two subarrays, right? And among those four uh, partition partitions, this one will give you the minimum of the largest sum among those subarrays, because this one will give you like 18s of all this, the maximum of those 18s of those subarray sums, right? Mm, yeah, this problem is kind of hard, yeah, but I'll try to explain uh, to you guys clearly. So I'm gonna use like two solutions today. I think first one is the DP, dynamic programming, and second one will be the binary search. Okay, let's get started. So first, dynamic programming, right? So with dynamic programming, so the most important thing for us is de to deduce the DPI sorry, DPI and J. I think since we have numbers and M here, so it's most likely we're gonna need two D arrays here, right? Equals to something else, right? So from DPI and J to get the DPI and J, we need to find a formula, right? To get this DPI and J from the previously result, right? Okay, so let's assume here, we have a number here, x, right? Let's assuming we have this kind of numbers. Let's add this number here, add this number, right? Basically, so the ij stands for with the current length of the integer I, right? That's the length of the numbers. J will be the current groups. Current groups will be zero or will be m, right? So this is m. This is the length of the numbers, right? This is going to be a number. So dpi and j means with the current numbers and current groups, what is the minimum of the largest sums subarrays uh, among all the subarrays. So how can we get that, right? And let's take a look. So with this one to be the current numbers, right? Uh, Here are the possible ways, right? Are the possible ways we can, so between the beginning and to the current numbers, we need to loop through each possible ways of uh, partition this arrays to the m minus one, right? Let's assume here we need to find like a place for a current subarray, right? So how many are possible arrays for the current subarray, right? There will be like, so that's why we need to loop through from the beginning to here. Basically, will be to construct, so the current subarray can be consist of from here, from here, from here, and here, right? That's all the possible subarrays we can we can partition for our current group, right? And so let's say we have decided, let's say we have this, like we decide from here, let's say this is K, right? Let's say we already have, we decide, okay, from K to I, this this gonna be our group, gonna be our group of M group, right? Then okay, so then what's the value of the okay, so what's the largest sum? What's the largest sum of this DP, right? It's gonna be uh the sum from K to I, right? Sum K to I plus DP what? DP uh DP, let's see. Yeah, DP here, DPK, right? DPK, that's the number starting from here, right? Starting from here, and then the M minus 1. Basically, we're separating this array into two parts. One part is here, the other part is the previous one, right? And we have this, we have the current sum, right? We have the current sum, and then we have the previously result. Previously result is this one. So we just need to get the minimum. Sorry, it's not a plus here. It's the minimum of that. We need to get the minimum. Sorry, not minimum, the maximum of this one first. The maximum of this one, because that will give us the maximum sum of the current partition, right? And among all those partitions, since K will be from 0 to I, right? We'll be getting the we'll be getting the minimum value for all the possibilities from 0 to I among all those maxes to the minimum, because if there's another K here, will be there gonna be have another max, right, of that current of that K partitions, like the maximum sum around for those arrays. And then in the end, we'll be summarizing, basically comparing all those maximum and to get the minimum value to be the current I and J. Okay, okay, let's try to code these things. Okay, so the n is gonna be the length of the nums, right? M is M, right? So for DP, we're gonna have like DP. Hmm. Since we're getting the minimum, right, in the end, so when we initialize this DP, we're gonna, for each element, we're gonna have like a system, we're gonna give it the maximum value, maximum. And it's gonna be the, yeah, it's gonna be M plus 1, yeah, for range N plus 1, right? And yeah, like I said, since we're going to need to calculate like a sum from k to I, right? A common way of doing that is we're gonna use a pre-sum arrays. Then we can just simply do a uh, subtract from the for those two sums to get the range sum we need, right? Basically, we're gonna have like a pre-sums, right? Gonna be the number of for zero, gonna be mm, the length of n, right? Okay, and we need to initialize that thing, right? Pre-sums. Let's see. Um, okay, fine. So, or we can just do a give it like another array here, another value here. It's easier for us to calculate that. Basically, for I numbers in enumerate, right, in this range here, we do a pre-sums, right? Equals to the current number I equals to the pre-sum, basically the previous one, right? Plus number. Okay. So that's the we're doing this so that the zero ones doesn't we don't need the number zeros. Or you know what? Let's do this. Yeah, let's do this. Since in the end we'll also be defining like a m plus one, n plus one. So for the pre-sum arrays, it's easier for us to also use like a n minus n plus one as the length. So that's how we calculate this like pre-sum. And then, like I said, we just need to loop the I in range of the n, right? N plus one. That's the number. That's the numbers. And then in inner loop, we're gonna loop through the I have range of the m plus one, right? That's the groups. So for each right, and for each I and j, what do? We need a third, basically, a third loop to range from to try all the possibilities for each number, right? And then in range uh, I plus one, in range of I, okay. So here it's gonna be a I, okay, that's fine because here since we're defining initialize with the n plus one, then with the numbers of I, we need to start from one. One means the length of I, the length of the number. It's not the index, it's one based. Same thing for here. So that's what this is a group one, right? For group zeros, it's we just simply ignore them. Yeah, for group zeros, I think that that won't be any valid answer there. So now for each of the I here, right? We we do what? So first we get the current max, right? The current max for dividing the dividing the race from zero to current to zero to I in at the kth position, right? It's gonna be the what? The max, right? The max number of the so since now we have the k to I, right? So what's the current array's sum from I to k, right? That's gonna be the pre-sum k minus pre-sums of I, right? I think sum I equals to j. Let me see. Oh, sorry. Here it should be I I minus k because I is greater than k, right? So that's the current sum, right? That's the current sum by splitting k from I to k to be the current array, right? And then what's the previous one? Then we need to find the previously dp, right? The dp will be with the number I is the number, I is the k minus 1. No, dpk, k to a j minus 1, j minus 1, yeah. So that's the previously k with the previous uh, num with the case partition, the and the group I j minus 1. Yeah, so here's the here is the range of k plus 1 to I think. Yeah, this is the k plus 1 to I, the range of that subarray, and then the previous result will be the dpk, and with a group with the current j group minus 1 because this thing represents the j's group, right? And this one, so then we need to get the maximum value between our current group and the previous group, right? Then that's our current value, and we just do what? We just for each of the current values, we do dp I and j, right? Equals to minimum, right? Among all of those things, we do a minimum of ij dot current max, right? That's how we do the dp, and in the end, we simply return the dp n and m, yeah. Pre-sums, okay. Uh, Here. Hmm. Uh, oh, I know why. So, yeah, here I think I'm reusing the same variables here. That's why to mess up with the following calculation here. So I have I have to make sure all of them is unique. Uh, oh, sorry. Yeah, because at the beginning we also need to define the zero, this one to be zero, right? That's our starting point because otherwise, since we initialize everything to be the biggest numbers, and we need a base case. Otherwise, right? Otherwise, here we'll be always getting the maximum number of these things, right? Because with zero zeros, basically means if there's no numbers and no uh, groups, the the minimum value we can get is zero, right? That's why we need this base case here. Let's run it here. Cool. As you can see here, this is not the fastest way because as you can see, the time complexity for this thing is going to be n plus o, like n times m times times n again, right? Because for each of this I here, we'll be looping through everything for this I. Basically, it's going to be n square, going to be n square, yeah, times m. That's the time complexity, and the space is the basically the m n times m, right? Because we're using a 2D array here to store everything here, and plus the another 1D array, but it's bounded. It's bound to a o, m, and n. So so for this thing, okay, so basically let's revisit this logic one more time. I know I didn't do a good job to explain this DP problem because for DP problem it is hard, right? Basically what we are doing here, so for each of the I and j, right, to be able to get the current I and j, which stands for the with current number I and the j's group, right? How can we get the values from previous result, right? So first thing to note is that we need to loop through all the previously possible ways of partition, right? Do the partition from 0 to I, right? This is all. We have a case possibilities to partition the previous the previous subgroup subarray with this to be the current group, and this will be the previously group. What I based on based on the k we chose here, right? So we use the presum to calculate. Okay, if we pick k to partition to do the partition, and then the j's group sum will be this, right? Will be the sum presum I minus the presum of k, and that's the current group. So how about the previous group? Because we need to get the largest sum among those groups, right? And the previously group's value will be the dp, right? The previous result will be dp the k, right? That's the position of k, since this one will be the k minus from k plus 1 to I. And so the previously number will be will be end with k, and the group will be j minus 1, right? And for each of them, I will need to uh, get the minimum among everything, among all the possible case. And then that's why we get a dp I and j. In the end, we simply return dp nm. That will be our final result. Okay, that's for dp. Okay, let's take a look at the binary search, right? As we can see here, the time complexity for the dynamic programming is not that good, but it's kind of a little bit more intuitive than the binary search, right? Okay, so with binary search, let's take a look. Let's try to solve this problem in another direction. So we need to get the minimum of the largest sum, right, among all those m sums, right? So what's the lower bound and upper bound? With binary search, we need to define the lower bound and upper bound, right? So the lower bound, so what's the minimum value, right? The minimum value will be if we divide the this subarray, so basically each value will be its own group, right? That's our lower bound because that will give us the minimum value of the largest sum here, right? So our minimum our lower bound will be the max of the sum of the sums of the numbers. right? And how about upper bound, lower bound, and upper bound? What's the upper bound? The upper bound will be what's the biggest value, right, for this minimum of largest sum among m subarrays. The upper bound will be there will be only one subarrays, right? That's going to be the sum of the numbers, right? So the lower bound will be each number will be its own like subarray, and that's why the lower bound of this minimum value will be the maximum between among all those values, and the upper bound will be only one subarray, and the value will be, of course, the sum of it, right? And then since you have a lower bound and upper bound, right, we just simply do a middle, like the middle with the lower bound and upper bound, and then with this middle sum, right, with this middle sum here, we will use a greedy method. Basically, with this middle sum, it means with this middle sum, uh, each group will try to uh, partition this group into a case into a case group, whereas each group uh, each group sum of this case group will be no greater than the mid sum, and we're trying to get as small of this case number as possible for this mid sum, right? So that's the greedy algorithm here, and once we have this k here, once we have this k number here, we compare the k with the m, right? So if k is greater than m, right? So if k is greater than m, what does it mean? It means that uh, okay, so remember we try to get this k number as small as possible. Even with that approach, if we're still having more groups than m, then it means this middle sum is too small, right? Which means we need to choose a bigger sum so that we can have like a k uh, equal to m, right? So in this case, basically the left will become the middle plus one, right? Else, right? How about else? Else means k is smaller or equal than m. Then we know, okay, so we have already got the answers we need, right? And then the right, not the answer we need. It's possible, so it has to be on the left side. But we need this middle because since the k is smaller, then the middle could be our answer, right? That's why we will be keeping this middle here. And in the end, we just simply return the right here, right? Because we are, as you can see, we're trying to get the minimum value of, right? So that's why we're trying to search to get the value as left as possible, right? That's why we are always trying to move this right to the left as far as possible. And each time we have a middle here, we do a greedy like partition to check the case here, and then we just keep moving, try to keep moving this right to the left until it meets to the left, and then we know that mid sum will be our answer, right? Okay, so let's try to code these things here. So left will be the max of the nums, right? Nums, and the right will be the minimum, sorry, will be the sum of the nums, right? That's our upper bound and the lower bound, right? And we simply do a while, right? While left is that's the basic the template of the binary search. Middle equals to what? The left plus right um, 2, right? And then okay, this is weird. Oh, here I think I made a mistake here. Yeah, cool. So and then we'll be getting like a pieces, right? We can get like how many subgroups we can subgroups from, right? From like a get subgroups, right? And then something, and then we'll be passing this middle to it, right? We'll be implementing this get subgroups later on. And if subgroups, like we said, is greater than k than m, right? Then we know this the middle we chose was too small, so we need to do a move this one to the we need to move the left pointer, right, forward. Else else we simply do a right equals to middle, right? In the end, we simply just return the right. And then let's try to implement this get subgroups, right? Is the is the sum, the uh, upper bound, okay, upper bound sum, okay. Yeah, I'll make it upper bound sum since the we're gonna use this sum to be as a upper bound because and since we're doing a search here, basically it means that each group in this with this sum cannot be each group sum cannot be greater than this upper bound sum here, right? It will count here 0, and how about the current sum 0, right? So we simply loop through the numbers in nums and current sum uh, number, right? If current sum is greater than the upper bound, right? Upper bound sum, then we know we need like another we need another groups, right? Plus one. And then meanwhile, we also need to because we know this one the current sum will not be fit in the previous group. Meanwhile, we'll also be updating the current sum is a num it's current num here, the num here. So and then in the end, we simply return the count plus one. So the reason we do a plus one is that for the last numbers here, right? Everything inside the last for the last numbers will be will be inside this the last group here. And yeah, and since we're doing like a left equals to mid plus one, we don't need to worry about uh, getting into an infinite loop in case of if the left and right are they're only like one number off, right? So try to search it. Yeah, as you can see, this approach is much faster. Because why? Because the time. Let's take a look at the time complexity here. So the time complexity of here is the and okay. So on the outside is the is a since we're doing the search, right? So the upper bound will be that. So it's going to be a log, the log of the what of sum, right? Of sum of the basically the log of right, right? Sum sum of numbers, right? So that's the outer bound, outer loop time complexity because we are doing the binary search in the range of the sum of numbers, right? How about the inner bound? So inside here, we simply loop through all the records, all the numbers in numbers, right? So it's going to be the n times n, right? So that's going to be the O of that. And since this numbers is, this is like the const, it's like even though it's kind of big, but this is kind of like if you do a log n, you can treat this one too close to a constant here. So this thing will be roughly equals to the ON, right? Comparing to the and also the space complexity will be O1, right? Because we're not using any extra spaces other than this left and right and the middle here, right? As you can see, comparing with this kind of dynamics approach with like the n squared times m, right? This binary search is much faster, but this binary search is not easy to come up with. Yeah, at least for me, it's really hard. Yeah, I think comparing with 410, there's another like very similar problem for this binary search. It's called divide chocolate. So for that, it's a like for the other one, it's completely opposite of this one. So for example, this one is getting the minimum of the largest, right? And the other, the divide chocolate, is getting the largest of the minimum. So, and that, if you guys are interested, you can take a look at that problem. That problem is using a similar approach at this one, but instead of but that in that problem, instead of using upper bound of sum, we are we're passing in a lower bound of sum. Basically, with this lower bound of sum, we're trying to get as many groups as possible. That each group will have at least this lower bound sum, and then we do a different, a little bit different of this in the binary search here. So yeah, at least for this problem, I think that should be pretty much I can think of. So again, so for the binary search, and we get the lower bound and upper bound, right? And then we get the middle point. And the way we're comparing, do it, move this cursor, cut it in half is to for the middle sum, we'll try to get uh, as less groups as possible, as possible. That's because with this greedy idea here, we're okay. So after getting the subgroups, we know this is the minimum groups we can get with this middle as upper bound, right? And if this like group is still greater more than the m, then we know, right? Then we know we need to increase the sum because we need a we need to get this the value to answer to equal to m, right? And otherwise we just move this right pointer, right, to the middle here. In the end, when the left meets the right, we simply return the m here. Uh, okay, guys, I think that's it for this problem. Yeah, I hope you guys can at least get some ideas or kind of understand the concept behind this problem. And cool. I think thank you so much for watching the videos, and I'll be seeing you guys soon. Bye bye.